In this video, we will show how to derive the integral representation of the zeta function. This is my zeta function, and this is the integral representation, where the real part of the complex number s, the real part is strictly greater than 1. Zeta is the zeta function. This notation is used in the bibliography, and gamma is the so-called gamma function. This integral representation formula is a very important result, and in general, in the Riemann hypothesis, there is this function zeta, and the hypothesis states that all the roots of the zeta function lie in a strip where the real part is equal to 1 divided by 2. Riemann has announced this conjecture. This hypothesis is the so-called Riemann hypothesis. There is $1 million prize from the Clay Institute in Massachusetts, in the United States of America, and it is a Millennium Prize problem. Let's see how to derive this integral representation formula. Let's define the function f of x to be 1 divided by e to the power of x minus 1, and the domain of this function is the whole R except for x equal to 0, where the denominator becomes 0. Then we take the Mellin transform of the function f of x. So we take the integral from 0 to infinity f of x to the power of s minus 1 dx. So it's 1 divided by, I substitute my function here inside the integral, and I also have this kernel of this is x to the power of s minus 1 dx. What I have to do here is take the common factor, the exponential, and decide I have 1 minus e to the power of minus x times x to the power of s minus 1 dx. The exponential, this function goes up, we flip the sign here on the top. Now, how do we write this integral? It's the integral from 0 to infinity e to the power of minus x divided by 1 minus e to the power of minus x to the power of s minus 1 dx. We write it in this way. This can be represented, this bit here, by infinite geometric series. We have the sum from n equals 0 to infinity e to the power of minus n times x to the s minus 1 dx. Because we have e to the minus x, then we change the index here, so n goes from 1, runs from 1 to infinity, e to the minus nx, x to the power of s minus 1 dx. So we have the summation from 1 to infinity, integral from 0 to infinity, x to the power of s minus 1, e to the power of minus nx dx. Now here we have to find a way to appear the gamma function. We simply change variable u equals nx. We change also the differential. So dx is 1 divided by n du. The bounds of integration remain the same because when I put x equal to 0, u is equal to 0, and x going to infinity, u goes to infinity. I have sum from 1 to infinity, integral from 0 to infinity. Now I solve for x, so from here x equals u divided by n to the power of s minus 1 e to the power of minus u 1 over n du. So it's the sum from 1 to infinity, integral from 0 to infinity, u to the power of s minus 1 e to the power of minus u du, and I also, in the denominator, I also have n to the power of s. It's the sum from n equals 1 to infinity, integral from 0 to infinity, u to the power of s minus 1 e to the minus u divided by n to the power of s du. Now I can take this 1 divided by n to the power of s outside the integral because the differential here is du. 1 divided by n to the power of s times the integral from 0 to infinity u to the power of s minus 1 e to the minus u du. And this is the gamma function, and this is the zeta function. So this is zeta of s, and this is my gamma function, gamma of s. The integral from 0 to infinity x to the power of s minus 1 divided by e to the power of x minus 1 dx equals zeta function of s, gamma of s. I solve with respect to the zeta function, and I have 1 divided by gamma of s times the integral from 0 to infinity x to the power of s minus 1 divided by e to the power of x minus 1 dx. This is the integral representation formula. For the function zeta of s, the zeta function, for when the real part of the complex number s is strictly greater than 1. And this concludes my proof.